Welcome to Desert Wanderers, produced by Salt and Light Radio. If you're new here, we bridge the gap between you and the person in the pew next to you. We have something new for you for the next couple of weeks with Dr. David Lamey. He is going to be producing a series of talks that will discuss the intersection of science and faith. He'll go over questions of the origin of the universe and genetic code and what God has to do with all of that. With this being said, if you've ever pondered the mysteries of life itself or the origin of the universe, go ahead and stay tuned for this episode. We hope you like it.
Hello everyone, I'm Dave Lamey, a physician and big-time science nerd, and this is the third talk I've put together on the intersection of science and faith. Today's talk will be on the Big Bang Theory. What does it claim? What does science really tell us about a beginning to the universe? And how does this intersect with Christian theology? As you know, the Big Bang Theory claims there's a beginning to the universe. But if you stop and understand what it really claims, it's quite shocking. It claims that at some point in the past, both time and space began to exist, and prior to the Big Bang, neither time nor space existed. It also claims that all matter and energy that exist in the universe today were created at that very moment. Let's think about how much matter that is. We're in the Milky Way galaxy, which has between 100 billion and 400 billion stars, and our sun is kind of an average star in our galaxy. But there's an estimated 100 billion to 2 trillion galaxies, and all of those stars, or at least most of them, are believed to have at least one, if not more, planets orbiting them. So that's quite a bit of matter. And yet the Big Bang Theory claims that all of that matter that exists in the universe today at some point in the past was packed into this very tiny, incredibly hot, dense state. In fact, it began as a size smaller than a single atom. So if you really think about the beginning of space-time, energy and matter in that fashion, it can be kind of hard to conceive, but that's what the Big Bang Theory claims. Throughout history, of course, philosophers and scientists have been thinking about and studying the universe, and there are three main questions they've tried to answer. How big is the universe? Is it infinitely large, or does it have a limit to it? Has it always been here? Is it eternal, or is there an actual beginning to the universe? And is it static, meaning are the stars relatively stable in their location, or is the universe in some way changing with time? Most scientists and philosophers throughout the ages have believed that the universe actually was eternal. This goes all the way back to Aristotle, who, with his logic and reason, believed it was eternal because to him it was completely illogical that matter could have been created out of nothing. And even up to Einstein, in the early part of the 20th century, he believed the universe was eternal. He also believed it was static, and he thought it was finite. Even the great St. Thomas Aquinas struggled with this question a bit. He was a 13th century theologian and philosopher, and arguably perhaps the greatest intellect in the history of Christianity. He struggled with this. He was very good at combining Greek logic and reason with Christian theology. And he said, on the one hand, logic and reason seem to point to an eternal universe, but his faith told him that there had to be a beginning. Again, most scientists have believed that the universe was eternal. The exception to this would have been in the 16th and 17th centuries with the scientific revolution. And I talked about this in my last talk. But the scientists leading the scientific revolution were virtually all very faithful Christians. And they believed that the universe had a beginning, but they believed this based on their theology and on scripture, and not because of scientific evidence. In my last talk, I discussed the things that happened in the 19th century that really drove a wedge between science and faith. And by the end of the 19th century and entering the 20th century, the vast majority of scientists held a materialist worldview. That's a belief that the fundamental reality that explains everything is the very existence of matter itself. And because matter exists and the laws of physics and chemistry acting on that, that is the explanation for everything that exists in reality. And so at the beginning of the 20th century, most scientists believed that the universe was eternal, that it was static, and they were a bit split on whether or not it was infinitely large or finite. That began to change with the proposal of the Big Bang Theory. The first person to propose that was a Belgian physicist and Catholic priest named Georges Lemaître. He came up with his theory, which he did not call the Big Bang. He called it the primeval atom. But he came up with it based on two separate lines of evidence. The first was some discoveries in astronomy where astronomers were beginning to see that there were other galaxies out there and that they were all moving away from each other. And also he used theoretical physics based on Einstein's theory of general relativity, which when the equations with that theory are solved, they point most likely to a dynamic universe. And based on this, he proposed an expanding universe that, going back in time, may have had a beginning. Now, I'd like to get into a lot more of the scientific detail that showed evidence from these two lines of reasoning. And I'll get a little bit nerdy here, but I'm going to try to keep this at a level that even if you've never had any courses in physics, you'll be able to follow it. The story really begins in 1912 with an astronomer named Vesto Slipher, who was working at an observatory in Flagstaff, Arizona. And he was looking up at what are called nebulae. And a nebula is a collection of space, dust, and gas that is associated with either the birth or a death of a star. But as he looked at some of these, he saw that they appeared to be moving away from us. How he found this was due to what's called the redshifting of the light coming from these nebulae. This gets to what's known as a Doppler effect, which you may have heard of. A Doppler effect works by either compressing or lengthening waves as we observe them. For example, if you're standing on a sidewalk and a motorcycle is approaching you, you're going to hear the sound of that motorcycle with a rather high pitch until it passes you, and instantly the sound, the pitch from the motorcycle drops down. And yet the person on the motorcycle, of course, never hears a change in the pitch. The reason you observe that is the sound waves coming off that motorcycle while it's approaching you, the sound waves are compressed. But as the motorcycle pulls away, the sound waves are lengthened, changing what you hear. The same thing happens with light. Light is made up of an electromagnetic energy, and the longer wavelengths of light are on the red end, and the short wavelengths are on the violet end. And when you pass light through a prism, it bends or refracts. And how much it bends depends on the wavelength. And that's the reason, of course, we see rainbows when sunlight passes through raindrops. Well, Slipher was observing these nebulae and passing the light through a prism which refracts the light. And that will give a pattern, what's called a spectral pattern, of the light. But he was seeing that some of these nebulae had that spectral pattern shifted toward the red, indicating that the source of light was moving away from us. He let other astronomers know at the time, and it raised quite a bit of excitement, no one quite knew what it meant, other than the fact that we probably don't live in a static universe. We live more in a dynamic one. Well, then in 1924, an American astronomer named Edwin Hubble, who you've probably heard of from the Hubble telescope named after him, he and his partner Milton Humason were working out of Caltech in Pasadena, and they were working at what's called the Mount Wilson Observatory in the mountains above Pasadena. Now, they had a much improved, much more powerful telescope, and when they looked up, they saw that what astronomers had been calling nebulae, some of these were actually entirely separate galaxies. Up until that point, we believed that the Milky Way was the only galaxy, but Hubble found that there were all these other galaxies out there, and what Slipher had been looking at were actually other galaxies. So he and his partner began plotting many different galaxies out there, and they were able to measure with the redshift technique how fast they were moving away, depending on how redshifted the light was. At the same time, Hubble was also measuring the distance to these other galaxies. It's fairly complicated how we can measure the distance from Earth to a star in our galaxy, or the distance from here to another galaxy. But a technique had been developed by an astronomer at Harvard named Henrietta Leavitt. And it basically, in very simplistic terms, relies on the brightness of what we're looking at. So with this formula to calculate distance, Hubble and his partner were calculating not only how fast things were moving away, but how far away they were from us. And when they plotted both the velocity and the distance on a graph, they found something quite remarkable. There was actually a linear relationship between how close something was to us and its speed that it was moving away. Things that were further away were moving faster, and if something were twice as far away from us, it was moving away twice as fast. So in this model then, they realized that the entire universe is expanding much like a balloon expands. And then imagining that all of that going back in time would have started in the same place at the same time. That was the first line of evidence that Father Lemaître had used for his theory. Einstein's theory of general relativity was published by Einstein in 1915. Prior to that, he had already published his theory of specific relativity. And in specific relativity, he explained how mass and energy are intimately related. And of course, everyone's heard the famous equation E equals mc squared. But in specific relativity, he also showed how space and time are intimately related. And in fact, now most astrophysicists talk about space-time, not space and time as separate entities. Well, in Einstein's theory of general relativity, he explained that gravity is essentially created by mass in the universe bending the fabric of space-time. The analogy people use to help understand this is a trampoline, and the fabric of the trampoline is flat. And then if you put a bowling ball on it, the fabric of the trampoline bends. If you put any other ball then on the trampoline, there'll be a force bringing the two balls toward each other. The gravity itself, as you know, had been discovered back in the 17th century and described in fairly good measure by Sir Isaac Newton, the famous apple falling from the tree, and gets him thinking about it. We're not sure if the apple falling is true or not, but he did research on gravity and gave us a pretty good understanding of it. And he explained that gravity exists throughout the universe, and it exists between any two separate bodies in the universe. And in his formula for gravity, as long as you know the mass of one object and the mass of the second object and the distance between them, you can calculate the force of gravitational attraction between those two bodies. And it turns out his formula for gravity is quite accurate in most situations, but it actually becomes inaccurate in certain extreme situations, like when you approach very dense masses like a black hole, or if objects are traveling incredibly fast. Then his formula for calculating gravity starts to become inaccurate. Einstein's theory of general relativity has all of these pretty complicated mathematical formulas attached to it that are called field equations. But these field equations do a much more accurate job at calculating gravity in some of these extreme situations. Well, when Einstein proposed his theory of general relativity, it created a problem in his own mind. He realized that if it were true that gravity should cause all matter in the universe to collapse in on itself, and ultimately there would be no space remaining between any of the matter, and yet we don't live in that kind of world. Now remember, his belief in the universe was that it was eternal and that it was static. And his theory then couldn't be true if the universe was eternal, because if time has always existed, that would give enough time for gravity to cause this complete collapse, and that's not the kind of universe we live in. So he somewhat arbitrarily imagined there had to be a force counteracting the force of gravity, and he called that the cosmological constant. And he put it in his formula, and he gave it a value that exactly balanced the force of gravity so that the universe itself would remain static. Well, then some physicists began working with his field equations. And in 1922, a physicist named Alexander Friedmann, a Russian physicist, solved some of these equations and realized that in reality, these equations lead to a dynamic universe. It would be almost impossible with these equations to have a static universe. And it could be a universe that's either expanding or collapsing, but not one that's staying the same. He communicated that with Einstein, but Einstein was pretty set at that point in his belief on a static eternal universe, and initially didn't think that Friedmann was correct with his results. George Lemaître then, in about 1927, came to the same conclusion. And at this point, Lemaître was also aware of some of the astronomy findings that Hubble was making. And there's an interesting story that in 1927, Einstein and Lemaître shared a taxi ride to a physics conference. And in that taxi ride, Lemaître shared with him his findings, along with some of the information about Hubble and what he was finding. And it appears that perhaps that was a time that Einstein began to think that maybe we live in a dynamic universe. In 1931, Einstein did travel out to California and visited Hubble at the Mount Wilson Observatory, and there he was able to observe and confirm for himself these astronomy findings. And he later said that his proposal of the cosmological constant to balance gravity was the greatest blunder in his career. So within a relatively short period of time, Lemaître publishes his theory, Hubble publishes his data, and Einstein comes out to the press and talks about what he has seen. And Einstein was quite famous around the world at that point in the early 1930s. So now there's this belief that we do live in an expanding universe, and if you calculate how fast it's expanding and run it in reverse, it all points to a beginning where all matter was in the same place at the same time in the past. Well, this was a radical idea to most scientists, and there was quite a bit of pushback, both from philosophical reasons, but also from some scientific reasons. In fact, the theory really didn't gain widespread acceptance until several decades later, which we'll talk about. The philosophical reasons for the pushback were really because of the theistic implications. I'll give you a couple examples of what people said about this. The famous British astrophysicist Sir Arthur Eddington, who was a colleague of Einstein's, he wrote in 1931, "I have no axe to grind. The notion of the beginning is repugnant to me. I simply do not believe that the present order of things started off with a bang. The expanding universe is preposterous, incredible. It leaves me cold." German chemist Walter Nernst wrote, "To deny the infinite duration of time would be to betray the very foundation of science." And Alan Sandage, an astronomer working out of San Diego, said, "It is such a strange conclusion, it cannot really be true." Now, as I said, Father George Lemaître called his theory the primeval atom theory. The term Big Bang came from a relatively famous astrophysicist in England named Sir Fred Hoyle. And he was on a BBC radio talk show in 1949, and he was committed to an eternal universe because he didn't like the theistic implications. And so he essentially mocked the people that were believing that there was a beginning to the universe, and he called it the Big Bang. And he did it in a derogatory way, but the term ended up sticking, and it's what we know today. Now, aside from the philosophical problems and theistic implications, there were some legitimate scientific reasons to be skeptical at first. The first was that the measurements that Hubble and Humason made gave us a calculation that the beginning of the universe would have been 1.9 billion years ago. But in the early 20th century, we already had what's known as radioisotope dating, which has to do with the radioactive decay of things, and knowing how fast that occurs, we can calculate how old something is. And with what's called uranium-lead decay, we already knew at the time the Big Bang was proposed that the Earth itself was about 4.5 billion years old. And this certainly is not consistent with a universe that's calculated to be 1.9 billion years. But as the measurements for both distance and velocity improved with time, the calculation of when the universe began kept getting revised, and it stands today at 13.8 billion years, plus or minus about 100 million years, but that objection obviously went away. The second objection came from the fact that the physicists working on the Big Bang theory, if it were true, they calculated what the early universe would have been like, a very hot, dense state. And they understood how hydrogen and some helium could have formed. Those are the smallest atomic elements. But they had no idea how any heavier atomic element could form. Where did carbon or oxygen or calcium or sodium or anything we need for a planet and for life, where did these heavier atomic elements come from? Well, the work that was done in nuclear physics, beginning really in the latter part of the 1930s, but really in the 40s, 50s, and 60s, both on nuclear fission and nuclear fusion, all of that scientific research helped us then discover where the heavy atomic elements came from. They come from nuclear fusion occurring in stars. Stars are essentially gigantic hydrogen nuclear fusion reactors, and they combine atoms, releasing energy, but forming these heavier atomic elements. The largest stars have the shortest lifespan of a star, and large stars end their life in what's called a supernova, a giant explosion, sending all of their matter out into space, and eventually gravity brings some of that together to create a new star and surrounding planets. And we can literally say that we are made up of stardust. And the third objection was the fact that the physicist, again, calculating the early universe, stated that it was incredibly hot and dense to begin with and expanding rapidly, and that it was relatively dark to begin with. And that's because it was so hot there weren't stable atoms. And because of this, the electrons are essentially flying all over the place, and a photon, which is a unit of energy creating light, photons would immediately run into an electron, and therefore no light was essentially emanating from the early universe. Well, at about 380,000 years, based on calculations, after the initial Big Bang, the universe would have cooled off enough for stable atoms to form. The electron orbits around stable atoms would stabilize and light could be released. And in fact, at that time, they calculated there would have been an immense, incredible release of light. So incredible that billions of years later, there should still be essentially a glow of that electromagnetic energy. And that's been termed cosmic microwave background radiation, CMB radiation. So CMB radiation was predicted and not initially found. Now, the CMB radiation was eventually found in 1965, and it was found actually by accident by two physicists named Penzias and Wilson, who were working on a giant antenna. And what they were doing was trying to improve satellite communication. But with this giant antenna, anywhere they pointed their antenna into space, they had a low level of static. And they didn't know what they were looking at first, but they looked into it and worked with some other physicists at Princeton University and ultimately discovered that what they were hearing or seeing was this CMB radiation. And they ended up getting a Nobel Prize in Physics for that. So once the CMB radiation was discovered in 1965, the vast majority of physicists agreed the Big Bang theory did appear to be true. But there was still a remaining question of what actually happened at the beginning. Did it actually come out of nothing at all, or did it come out of something that might have been pre-existing? In the early 1970s, Stephen Hawking, who you most likely have heard of, a famous British astrophysicist, he suffered from ALS, Lou Gehrig's disease, and became quite well known around the world. He and his colleagues, Roger Penrose and George Ellis, were working also with Einstein's theory of relativity and the field equations. And earlier physicists like Lemaître and Friedmann had put some constraints on some of the variables in those field equations to make the math a little less difficult. Well, Hawking and his colleagues didn't do that. They left this wide open, and it came to what we now call the Singularity theorem. Basically, again, using the theory of general relativity, they showed that as you go backwards in time, the curvature of the universe gets tighter and tighter and tighter, and eventually the curvature reaches infinity. Well, any sphere with a curvature of infinity equals zero space. And because space and time are intimately connected, no space means no time, hence proof of a beginning of space and time. And also, if you can imagine how much matter you can put in zero space, it equals exactly zero. So the Singularity theorem essentially proved that space, time, energy, and matter began at the beginning, at the Big Bang. But it didn't absolutely prove it. There was still a reason that there wasn't absolute proof, and that is the theory of general relativity and the laws of physics that are associated with it. They break down when you get to the very smallest level, immediately after the Big Bang occurred. The laws of physics actually break down. And so that leaves the door slightly open for some other possibility besides creation out of nothing. I'll now go over some of the theories that have been proposed either before or currently that try to give us either an explanation that the universe itself is eternal, or perhaps that there is some material explanation for its beginning. The first was called the steady state theory. This was proposed by Sir Fred Hoyle, the same guy who coined the term Big Bang. He proposed this, and his colleagues, and his theory was that yes, we acknowledge the universe is expanding, but he theorized that perhaps something was occurring in empty space as the universe expanded to create new matter. And in this way, you could envision a universe that's infinitely large and goes back eternally in time. Well, that actually became a popular theory until the CMB radiation was discovered in 1965. The CMB radiation was entirely consistent with the Big Bang theory. It was not at all consistent with that theory. The next theory that became popular was known as the oscillating or bouncing universe theory. And this envisions a universe that goes through cycles of a big bang followed by a big crunch and back and forth, and that perhaps this could be going on for eternity. This ran into big trouble, though, with entropy and the second law of thermodynamics. In the second law of thermodynamics, we know that entropy is always increasing, which means that energy available to do work is always decreasing. Therefore, if a cyclical universe was a possibility, each cycle would have less energy available to do work, and each bounce, so to speak, would diminish, and eventually the bouncing would stop. Now, it's possible that this is happening, but it's entirely inconsistent with an eternal universe, because eternity would give us enough time for that bouncing to stop. You can envision dropping a basketball on a gym floor, and it's going to bounce for so long, and each one gets less and less until it's finally at rest. The next model that became popular was based on something called inflationary theory. There were several variations of this model, and this became popular in the early 1990s. And inflationary theory envisions a theoretical concept called an inflation field, which can essentially create a new bubble universe off of a pre-existing universe. And therefore, one can envision a large number, maybe even an infinite number of universes that have existed for eternity. This is still under some consideration, but it has run into a major problem where even if this were true, we now know for sure that there would be a beginning to all of this. This is based on a discovery made in 2003 by three physicists named Arvin Boyd, Alan Guth, and Alexander Vilenkin. They came up with what we today call the Borde-Guth-Vilenkin theorem. And this is a mathematical proof based on Einstein's theory of specific relativity. And they essentially left all variables wide open, not imagining any constraints to energy, to spatial configuration or volume or gravity. And in this mathematical proof, they showed that any model of a universe that is on average expanding has to have a beginning. It is complicated, and it's based on the limit of the speed of light. And I won't spend a lot of time explaining all that, but it is proof. It's not theory. And so any inflationary model has a problem in that it directly points to a beginning the universe in time. The next model that has been somewhat popular and is discussed these days is called quantum cosmology. This comes out of what we call quantum physics. And quantum physics is the study of matter at the smallest levels, at the atomic and subatomic levels. And many of you may not know this, but quantum physics, quantum mechanics shows that matter at this very smallest level behaves in very weird, unpredictable, and peculiar ways. For example, in an atom, we have a nucleus of a proton or proton and neutrons with one or more electrons orbiting it. But quantum mechanics shows us that that electron orbiting the nucleus can be at multiple different places simultaneously. Or when we look at some of these subatomic particles, they behave both as a wave and as a particle. And sometimes just the very fact of us observing them will cause their behavior to change. And this seems counterintuitive, but in fact, this is what we know from quantum physics. Well, using the laws of quantum physics, some physicists have come up with this idea of quantum cosmology, imagining the universe coming out of what's called a quantum fluctuation. And this is essentially what they're saying is the universe didn't come out of nothing, and it didn't necessarily come out of pre-existing matter, but something in between. What they're actually proposing is that the universe essentially came out of a set of mathematical formulas that are associated with the laws of quantum mechanics. Now, on the face of it, to most people, that would seem like an absurdity, but it's taken seriously by some very smart physicists. But even if this could be true, it has its own theistic implication. Math is an abstract concept that really only exists in mind. We can write it and use symbols to show it, but math is truly an abstract concept that exists in mind. And Alexander Vilenkin, who we talked about a moment ago with the Borguth-Vilenkin theorem, he has been a proponent of this theory, but he even recognized this potential theistic implication of their theory. He wrote, quote, "Does this mean that the laws are not mere descriptions of reality? The laws are expressed in the form of mathematical equations. If the medium of mathematics is the mind, does this mean that mind should predate the universe?" Unquote. So let's step away from science for just a minute. I'll wrap up shortly here, but let's talk for just a moment about logic and reason, and specifically about something we call abductive reasoning. I'll use an example that's commonly used to help explain abductive reasoning for those who may not be familiar with it, but that is the story of the turtle on the fence post. You're walking through nature one day, and you come across a turtle perched up on top of the fence post. You have no idea how the turtle got up there, but you can use your imagination to come up with as many different hypotheses, as many different explanations as possible. So I'll throw out a few. Let's say maybe you think that someone else was taking a walk out there and they, for whatever reason, decided to pick up the turtle and set him up on top of the fence post. Or maybe there is something we don't know about that caused a fence post that was buried under the ground to rise up through the ground right at the time the turtle happened to be in that very location. Or maybe the turtle stepped in something incredibly sticky and managed to crawl himself up on top of that fence post. Or maybe an animal or a bird grabbed a turtle egg and set it up there, and ultimately the egg hatched, and over time animals or birds, for whatever reason, decided to keep feeding it, and he's lived his life on top of the fence post. I mean, we can keep coming up with hypotheses, with explanations using our imagination. But at some point we have to stop and use our common sense and go, what makes the most sense? What is a mechanism that we know could actually cause a turtle to be perched upon the fence post, and therefore what is the most likely explanation for what we have just seen? In the end, we won't know 100% how the turtle got up there, but we can come to what is the most likely explanation. So, in summary, we know the universe began to expand 13.8 billion years ago from a hot, dense state, and the evidence is very compelling and yet not necessarily 100% conclusive that it began out of nothing, but that is where the evidence takes us. And when we look at the competing theories that have been or continue to be proposed, they all either point themselves to a beginning, perhaps a separate beginning, but nevertheless a beginning, or they have theistic implications, or they're about as likely as some of my explanations for how the turtle got on top of the fence post. So the scientific evidence today, combined with our logic and reason, points to a creator out of nothing. Creatio ex nihilo is the Latin term for creation out of nothing. We can't prove this, but the evidence, logic, and reason is quite overwhelming for this. And so we know that space and time began 13.8 billion years ago, and all matter and energy were created at that time. And when you think about supernatural events, what we call miracles, that's probably the greatest of them all. I want to thank you for hanging in there with me today. I know this has been lengthy, but you can tell I'm a nerd with this stuff. I enjoy it. So thanks for hanging in there. Stay tuned for further discussions on the intersection of science and faith. Have a wonderful day.
Thank you for tuning in to this episode of Desert Wanderers. If you liked it, give us a thumbs up as well as subscribe down below. We're produced by Salt and Light Radio, so you can find us on social platforms at Salt and Light Radio or Desert Wanderers Podcast. We produce episodes every week and we launch them for you on Wednesdays. So make sure to tune in for next week's episode and we'll see you then.